So today we're going to talk about the geometric distribution. But to do that, I'm going to start by reminding you about the binomial distribution. In a binomial setting, the number of trials is fixed in advance. And you have a binomial random variable that counts the number of successes. We're counting the number of successes. So what might the number of successes be? Well, it could be anything from 0 up to the number of trials, right? Because even though you have a set success and failure defined, you might never get a success. So the number of successes might be 0. Are you with me? You might get all successes, so the number of successes would be n, your number of trials, okay? In other situations, sometimes the goal is to repeat a process until you get success, and then you can stop. For example, let's say you're playing Monopoly, and you need to get out of jail. What do you have to do to get out of jail?
Doubles.
You have to roll doubles. Once you roll doubles, guess what? You're done trying to roll doubles. You are now out of jail. You have successfully gotten out of jail. So you roll a pair of dice until you get doubles, then you can stop. Or let's say you are doing a basketball drill and maybe your coach says you have to keep trying to shoot a three-pointer until you make one. Once you make a three-pointer, you're good. You can stop that drill. That would be a situation where you're trying to do something until you succeed. You keep going to that roulette table and you sure love the number 15 and you just keep placing a dollar bet on number 15 until you win. Once you win, you're going to take your $36 and leave because that's how much you would win. Maybe your AP stats teacher told you have to roll dice until you get a five dice that are the same and you got a Yahtzee. And so you roll 5 dice until you get a Yahtzee. For those of you who got a Yahtzee, did you keep rolling after that? No, because at that point you had succeeded, you were done, you were out. I don't have to keep doing this. This is all geometric. So geometric is when you perform independent trials of the same chance process. You record the number of those trials it takes to get one success. So you are going to fail every time before that, and then success, and you're done. That is a geometric distribution. So a geometric distribution is going to count, or it's going to have a probability of success of p, and you are going to have possible values of 1, 2, 3. It doesn't start at 0 because you cannot have 0 trials if you don't, or you cannot have 0 successes if you don't try. So you have to at least try once. Maybe you get your success on the very first try, but you have to at least try once. So it's always going to start at 1. Okay? All right, so in a geometric distribution, we have 4 conditions. The first one is we have to have a binary success and failure situation. So we have to have a binary success and failure situation. So same kind of deal as binomial, right? You have to have a clear success and a clear failure. You do have to have independent trials. Okay, now, obviously, there's not going to be an n here because we're not doing number of trials is set. We're doing trials until success. But we still have the qualification that our success probability is fixed. So instead of bins, what do we got? Bits. If bits is what you have trials until success. Instead of a fixed number of trials, you have geometric, okay? We're going to do an example so you guys will kind of hear how it will sound if it's something geometric. The parameters. Now, the parameters for a geometric distribution. Obviously, there's not an n. So for a geometric distribution, you just have one parameter, and it is the probability of success. A geometric distribution only has one parameter, and it is the probability of success. Okay? All right. Everybody good so far? All right, I'll take that as a yes. All right, the formulas. All right, so I finally gave you guys your own copy of the AP Statistics formula chart. So just real quick, I will go through what these are. At the top, you have your descriptive statistics. This is basically chapters 1 through 3. This is the formula chart you'll get on the AP exam, okay? X bar, what is X bar? The mean. So there's the formula for the mean. We usually use our calculator. S sub X, what is S sub X? Standard deviation. Again, there's the formula. We usually use our calculator. Y hat. There is your formula for linear regression. Y hat equals A plus BX. We have Y bar equals A plus BX bar, and B equals R times S of Y over S of X. Those were those formulas you had to use with the summary of the statistics in order to get the equation of the line. It was on the Chapter 3 test. It was the question about Miss Lakey and her car washes, helping her with her having to pay for repairs on her car. Those were the equations you had to use to get the equation. There's R. There's our correlation coefficient formula. We never use that formula, honestly. I don't even know why it's on here. Probability. Probability. There's your two probability formulas that are on the formula chart. Again, remember that the probability of A and B is just the rearranged formula, the second formula there. All right, and then we go into our probability distributions, which is this chapter. The first one says discrete random variable. So our very first thing we talked about was a discrete random variable. That was a countable variable that did not have a set number of trials. But usually you would get a chart that told you all of your different probabilities. That's when we used L1 and L2, and we did stat calc 1, and we put a frequency of L2. That's a discrete random variable. The formula that your calculator uses to get that mean and standard deviation is right here. So mean is there and standard deviation is right there. And then, look, there's your binomial formulas. If X, it literally says if X has a binomial formula or binomial distribution with parameters of N and P, here's your formula for the binomial. N choose X, P to the X power, 1 minus P is N minus X, and then X can be anything from 0 up to N. Your mean is N times P. Your standard deviation is the square root of N times P times 1 minus P. Whee! And then it says geometric. Here are your geometric probability formulas. So let's go ahead and write down what it says. For geometric, it says the probability that X equals X is equal to 1 minus P to the X minus 1 times P. Let's break this formula down real quick. Make sure you guys understand what it's doing. So X, what is X? This is the, so on this, it is the number of success, but it's like the number of trials that you got success. So this is the number of trial success was achieved. This is what trial was success achieved on. So like this would be, like let's say I said, what's the probability you got Yahtzee on the 10th roll? Then the X would be 10 because the 10th trial was when you got the success. Okay. Now, look at 1 minus P. You guys all should know what is 1 minus P. That is the probability of failure, right? So 1 minus P is the probability of failure. This is the probability of failure. Now, I raise that to the power of X minus 1. So, if I am looking for my first success to be on my 10th trial, then how many failures did I have? 9, X minus 1. So this is how many failures did you have? Well, you had all the failures up until that last success. Okay, so X minus 1, that's just how many failures did you have. Okay, so this is your number of failures. And then you have P. What does P stand for? This is your probability of success. You guys, notice that that does not have an exponent on it. Why not?
Because it's 1.
It's only going to happen one time, right? You are going to fail, succeed, and stop. You're not going to keep trying to get more successes. So for a geometric distribution, it's actually a pretty easy formula. It's what's the probability you fail? How many times did you fail before you got your last success probability? Okay? That's your formula for geometric. Now, your calculator will do this for you. Your calculator will do this for you under second VARS. If you guys go to second VARS. If you go to second VARS, you shall see the, if you go second VARS and you scroll way down, I think it's the last two on there. So you've got the same situation as we had with binomial. If you are looking for an exact number of trials until success, you would use geometric PDF. Geometric PDF. The only two things your calculator wants to know is what is the probability of success and what trial do you want success on? What is the X? So that you can use that instead of using the formula.
What was the last part?
This is going to be the probability of success, and this is what trial did you get success on? What trial was the success? Okay? Just like binomial, geometric has a CDF command as well. This is the probability that X is, anybody have a guess what symbol it uses? Less than or equal to. This is going to be geomet CDF. Again, it's only going to ask for two things. Now, let me say to you guys what it would sound like. How do you distinguish the difference between these two? I'm going to use the Yahtzee as an example. Because, by the way, Yahtzee was geometric. Because once you got Yahtzee, you stopped. So, this would be, what is the probability you get Yahtzee on the 10th roll? This one would be, what's the probability you get Yahtzee within the first 10 rolls? Did you hear the difference? This one, I have to get the Yahtzee on the 10th roll. This one, I need to get it within the first 10. So I could get it on the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, or 10th roll. So this is going to accumulate all those probabilities up to 10. Okay? That is the difference between those two. Do you guys have any questions on those?
Would the geometric CDF always have a higher probability than the other one?
Yes, because you're accumulating up to that number. Yes, absolutely. Very good. Very good. I did forget to write these down for you guys on your paper. They are obviously on your formula chart. But the mean of a geometric distribution is 1 over P. It's 1 over the probability of success. The mean of a geometric situation is 1 over P. The standard deviation of a geometric distribution. On the top of the fraction, we have the square root of 1 minus P. The square root is only on the top of the fraction. That's slightly different than what we normally see. And then we divide by P on the bottom. So those are on your formula chart. I'm going to be honest with you guys. Geometric distributions show up very rarely, and usually it's just in the context of, is this situation binomial or geometric in like a multiple choice problem? And it would then go through like telling you all the situation, and you just have to see, is it a set number of trials, or are we doing something till we succeed? That's about it. You guys will see some of those questions in your sapling, by the way. All right, let's do this example. Last page of 2023. Woo! Let's go! And I am going to use Yahtzee because I know you guys hate me for that thing. So we're going to just go ahead and rub it in your face some more. It's going to be great. Love you guys. All right. Suppose you roll 5 fair 6-sided dice until you get Yahtzee. Let y equal the number of rolls it takes. Note that the probability of getting a Yahtzee on any roll is 1 out of 1296. Show that this is geometric. How are you going to show it's geometric? Bits. All right. Is it binary? Do you have clear success? What's success? Yahtzee. What's failure? Come on in.
I have my glasses a little crumpled.
Can you get under there?
Oh, yeah.
Sorry, I smell like whipped cream. All right. Cool, thanks.
Yeah, please.
Failure is not a Yahtzee. Not a Yahtzee. I, what does I stand for? Is each roll independent? Yep. Independent rolls. All right, now what are we going to check? Do we have trials until success? Well, that's what it says in the problem. It says it says roll the dice until you succeed. So boom, we do have trials until success.
So it doesn't, the 1236.
What's an example of it not being a trial success?
If it tells you you're going to roll 100 times, so it gives you a set number of trials. Yeah, that's binomial. This one is, it would literally say you're going to do this until you succeed. Yep. And then S is our same one as it was for binomial. So our probability of success is
1/1296.
good. 1 over 1296. Perfect. So guess what? This is geometric. And our only parameter is P equals 1 over 1296. So there's our geometric distribution with that parameter.
So I'm a little bit confused about like one thing.
Yep.
So you said that it has to like be trial to successfully geometric,
Yes.
but why is it for the equation for the geometric PDF? That's like the equal.
Right, so the equal sign on a geometric PDF means that you're defining when you get the success. So saying, I'm going to get Yahtzee on roll number 10, or I'm going to get Yahtzee on roll number 20. What's the probability that that happens?
Okay, I thought it was more like the binomial.
Oh, no. All right, cool. So here's the question. What is the probability that Yahtzee equals 5? Meaning, what's the probability you get the Yahtzee on the 5th roll? So the probability that Y equals 5 is going to be, what would you use? PDF. So geometric PDF. It's asking you for the probability of success. And you can straight put in that fraction, 1 over 1296, right in your calculator. And then it's asking you for the X value. Basically, it's asking you, what trial do you think you're getting success on? Well, we think we're getting it on number 5. You guys should not be surprised that these probabilities are going to be pretty small, right? Think about it. I am defining an exact moment that I'm going to get Yahtzee, right? So what's the probability that you get Yahtzee on the 5th exact roll? Good. 7.69 times 10 to the negative 4th, which is equivalent to 0.000769. Okay? Now, I do want to show you guys the formula just in case you wanted to recognize it. It's actually, again, very easy, right? So, the probability of failure. If the probability of success is 1 over 1296, what's the probability of failure? 1295 over 1296. And in this situation, how many times do I have to fail? 4. And then what is going to happen? I'm going to get that Yahtzee. And so that is the formula right there that goes with this. It's a super easy formula. You fail 4 times, then you succeed. Done.
Okay.
That's what your calculator calculated for you.
So is that gonna be a question? Like, what's the formula?
They don't usually put that formula on there. They really focus more on binomial. Binomial is a little bit of a bigger and more common idea because it matches similarly to a normal sometimes. But it's fair game. So, okay, last 2 questions. Actually, there's 3 more because I'm adding one to, but it's fine. Find the probability that a student gets a Yahtzee within the first 100 rolls.
So that's
Now, when can they get it? They could get it on the first roll, or the 7th roll, or the 23rd, or the 52nd, or the 63rd. They can get it any of those times, right? So we're saying, what's the probability that they get it sometime within that first 100?
So doesn't that mean it's not bits?
It actually is, because I'm saying, what's the probability that I get my first success within the first 100? So I am saying, like, what's the probability that it takes me either 1 or 2 or 3 or 4? So it's like you're accumulating all these. What's the probability it takes me 1 until success, then or 2 until success, or 3 until success? So it's basically saying, what's the probability that sometime in your first 100 rolls, you're getting your first success? Still, if I get success at 22, I'm stopping. But it might take me 27, or it might take me 35.
So then, what is it not bits? Like,
So if it were to say, a student rolls 100 times, find the probability that 10 of them are successes. So you have to have two numbers. You have to have a set number of trials, and then how many of those trials would be successful. Okay, so this is going to be the probability that x is less than or equal to 100. This is the probability that x is less than or equal to 100. This is the probability that my first success is any time in the first 100. I'm not counting a number of successes in 100 trials. I'm saying, what's the probability that my first success is sometime in that first 100? Okay, because this matches the symbol that we need, we can go straight to geometric CDF. The probability of success?
1 over 12 minus 1.
Good. X. X is, what is the number of successes we are looking, what is the roll that we are looking to get our first success within? 100. Plug that in. So I'm about to show you guys the probability that you were going to get Yahtzee sometime in the first 100 rolls. 0.0743. That means if you got your Yahtzee within the first 100 rolls, you're special, because there was only a 7.5% chance that you were going to get Yahtzee sometime in that first 100 rolls. So you're pretty special. Find the probability that a student gets a Yahtzee after the 1,000th roll. So this is the probability that your first success happens after 1,000. Okay? All right, what do you guys notice about this sign? Woo, we need to flip this puppy. So 1 minus the probability that x is less than or equal to?
999.
What?
Is it not?
Oh.
Wow.
So if we are going more than 1,000, that's 1,001 or more. So what am I taking off? 1,000 or down. So this is saying, like, okay, so 998, 999, 1,000, 1,001, 1,002, blah, 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 blah. Okay. So this says the probability that x is greater than 1,000. That is from 1,001 up, right? Greater than 1,000 is 1,001 or higher. So I want to take away 1,000 down. So this is going to be less than or equal to 1,000. That would have been different if there had been an equal sign right here. Then it would have been 999.
Wait, so it's still 1,000.
It is. All right, so 1 minus
Well,
That was a good point.
geometric CDF. P equals, what does P equal? 1 over 1296. X equals 1,000. You did not subtract from 1. You guys, do you guys recognize what just happened? I just told you there's almost a 50% chance it would take you more than 1,000 rolls to get that Yahtzee. You're welcome. So again, let me say this again. We were finding the probability that x is greater than 1,000. What is the number that is greater than 1,000? 1,001, okay? So I'm trying to find the probability of 1,001 or more. It takes me 1,001 rolls or more. I can't do that in my calculator, so I have to flip the sign, 1 minus. And if I'm looking for 1,001 or more, then I'm taking away from 1, 1,000 or down. But if this had said greater than or equal to, then I would have included the 1,000, and then that number would have been 999. Y'all see that difference?
Yes.
Okay.
Sure.
Do you see it?
No. It's okay. We're checking.
so
All right. I have one more. Yes.
Could you just do like 1295 or 1296 to the 1,000th power?
So that would be to get equal to 1,000.
Let's get the same answer though.
What is 1295 over 1296? What is that to the 1,000th power?
0.4621. It's the same.
Yeah.
So it is only the probability of failure. Is that correct?
What is going on? So,
I didn't get
better than the teacher.
Yeah.
That sounds like a conversation I don't need to
Because
bring
it's
up.
like the first 1,000 would be failures to get that.
Sounds like I'm interrupting.
Correct. So
So that just is like.
if the first, so if we do 12 divided by 1296 equals that to the 1,000th power. So that means you have failed 1,000 times. Oh, and you have yet to get success. So yes, that would work actually. Yes. Because you would not multiply by the probability of success yet because you haven't gotten it. So you have failed for 1,000 times. At some point after 1,000, you're going to succeed. So yes, if you just take the probability of failure and raise it to the 1,000th power, which is exactly what you've done here. You have failed 1,000 times, and sometime after that, you're going to succeed. So yes, if you take the probability of failure and raise it to the 1,000th power, you do get that same answer. Yes, absolutely.
So that answer, I put in the calculator and I didn't get
Let's look at that in just a second. I will come look at that in just a second. All right, I want you guys to add this question to the bottom. Add this question to the bottom. E. This is E. Find the mean and the standard deviation of the Yahtzee distribution, which we know is geometric. Find the mean and the standard deviation of the Yahtzee distribution, which is geometric. All right, we're going to find the mean and the standard deviation. These formulas are on your formula chart. The mean is 1 over P. Now, let's think about what that really is. 1 over P is 1 over, and then what is P? 1 over 1296. You guys, you have a 1 divided by a fraction. Do you guys remember what that does? It flips it. It's reciprocal, right? So what is the mean of this Yahtzee distribution? 1296. Let's think about that. That means that we think we're going to get Yahtzee on average in 1296 rolls. Okay? Okay? Now, what's the standard deviation? This is the one that's a little crazy. The square root of 1 minus P divided by P. You got to be really careful when you plug this in your calculator. I would highly recommend you do the top first, then get the answer, and then divide by the 1 over at the bottom. Because, again, you've got a fraction on the bottom of the fraction. And you're going to think this is a crazy answer. But it's actually not. Are you getting a really big number? 1295.5? You guys, do you know what this means? On average, you should get Yahtzee within 1,296 rolls, give or take 1,296 rolls, which means you should get Yahtzee sometime between your first roll and your 25th, 100th roll. I set you up for failure. I'm so sorry. Because I'm mean. Okay. Everybody good? Yes. Perfect.